Hi friends, I wanted to share with you how to do free body diagrams. What I'm looking at is page 2 in our practice packet, and what you should have out while you're working on this is your notes from 9/11, where we listed different types of forces as well as information about the net force. I'm going to start with number 1, and it says the box sits motionless on the floor. We're asked to draw a free body diagram of this. So when we draw free body diagrams, we start with a dot, and then we draw arrows to represent the forces acting on that. So since the box is sitting on the floor, I'm going to draw a dotted line to represent the surface. This is part of the free body diagram for any objects that are sitting on a surface. So as I look down my list of forces in my notes, I see the force of gravity, and the force of gravity is always present when an object is on Earth. So I'm going to start by drawing an arrow in the down direction coming from my dot, and I'm going to label it FG to represent the force of gravity. Now I know since this box is sitting motionless, it is at rest or it is still. And if it's at rest or still, that means that the net force, F net, is equal to 0. And so that means that I have to have balanced forces. So far, I have a force in the down direction. I'm going to have a force in the up direction to balance that. When I look down my list of forces, I see the normal force. That's a force due to a surface. Sometimes it's called a support force. Whenever an object sits on a surface, for example, the floor, it'll have a normal force acting on it in the perpendicular direction to that surface. So this force will go in the up direction. So I'll draw an up arrow to represent the normal force. I'll label it Fn. Since the net force meaning the total of all forces acting on an object, is 0, then I know that these forces have to be equal to each other in size and opposite in direction. I'm going to draw a tick mark on them to represent that they're the same size. I'm not going to put any forces in the horizontal direction because there's nothing else acting on this object. Once I've completed my free body diagram, then I need to write the net force equations in the x and the y direction. The net force equation is variable form for all of the forces acting on the object. So in the x direction, that means horizontal, there are no forces. So I'm going to set this equal to 0 newtons. In the y direction is vertical, I do have forces. I'm going to write all of the forces in the positive direction. Positive direction would be up or to the right. In this case, up, Fn. And then I'm going to subtract all of the forces in the negative direction. In this case, the only force in the negative direction is the force of gravity. So the F net y, that means the net force in the y direction, is equal to the normal force minus the force of gravity. We know also because this object is motionless, it's at rest, it must have a net force of 0 newtons. The last part when you're completing a free body diagram is draw the arrows to represent the direction of velocity, acceleration, and net force. I'm going to start with net force since we just wrote that that was equal to 0. When the net force is 0 and the object is motionless or at rest, we know it must have no velocity and no acceleration. So instead of arrows, I'll draw zeros. Let's try one more example. I'm going to do example 3 because it also includes some forces in the horizontal direction. So for example 3, we have to draw a free body diagram of a heavy crate being pulled horizontally with a person by a person with a force that's parallel to the floor. The crate doesn't move. I will start with my dot. A free body diagram also always starts with a dot that represents the force. Since this heavy crate is on Earth, I'm going to draw an arrow in the down direction representing the force of gravity. Every time we draw an arrow on our free body diagrams, it points away from the dot, and we label it with the type of force. I forgot to draw my surface, so I'll draw that dotted line to represent the surface. And now, since I've remembered there's a surface, there must be a normal force. The normal force is perpendicular to the surface, so it goes up, and we label this Fn. We know our crate is not moving, so the forces are balanced. I'm going to put dash marks to represent that those two forces are equal. I'm not quite done yet. This says that the heavy crate is pulled horizontally by a person with a force that's parallel to the floor. And I can see from the picture that that person is pulling to the right. I'm going to draw a force to the right and label it F pull to represent the pull force. Now, I know that this crate is not moving. Since it's not moving, it must have an equal and opposite force in the other direction. When I look at my list of forces in my notes, I see the force of friction. The force of friction, FF, always goes parallel to the surface and opposes motion. If the pull is to the right, then the force of friction will go to the left. So I'll draw my force of friction arrow, label it FF, and I know that it's equal in size to the pull force. So I'm going to use 2 dashes to represent this example. Now my free body diagram is done. I can write the net force equations. For net force in the x direction, I want to take everything that's in the positive direction. So far, that's only the pull force. And then subtract everything that's in the negative direction. That's my force of friction. Notice for the x, I only use what's in the horizontal direction. I can set this equal to 0 because the object is not moving. For the F net in the y direction, I want to take everything in the up direction and subtract everything in the down direction. The net force in the vertical direction, the y direction, is normal force minus force of gravity. And again, I will set it equal to 0 because the object is not moving. And we know when an object is at rest, the net force is 0. My last step is to draw arrows to represent the direction of velocity, acceleration, and net force. Since the crate does not move, velocity is 0, acceleration is 0, and net force is 0.